Welcome to this next class on chemical kinetics. So, before I start with the proceedings of today's class, I will as usual I will do a brief recap of what we did in the last class, and this is what, if you would remember, we were talking about the kinetic analysis of experimental data, and one of the things we started with was the average rate. So, the average rate, as you can see out here, is defined by the concentration difference over a defined time difference or interval, which is delta C over delta T, and if it is obviously reaction, then this average rate is always preceded, or this gradient is preceded by a minus sign. Okay. Now, apart from this average rate, what we also have is something known as instantaneous rate. So, this was the next one which we were discussing. And what is the instantaneous rate? The instantaneous rate, as defined by the word instantaneous, means that we are trying to figure out the rate at any given instant, right. For example, whether it is T1, T2, T3 and so on. If if you see these, remember these dots or green dots, if these are your respective times, then what you would do is, to get the instantaneous rate, you would draw a tangent at that point itself. See, for example, if you would try to get the instantaneous rate out here, right, which is defined as T1, then you would draw a tangent at T1, and what will happen is, then this R instantaneous, the rate which is the instantaneous rate, is equal to the negative of the d of R over d of T, where R is your reactant and in brackets it means the concentration of the reactant. Okay. So, the instantaneous rate is also a very important feature, it is one which is mostly used, and as I was saying just now, the instantaneous rate is achieved by or obtained by drawing a tangent at that instant or at that time point, which is T1, and from there we take the slope of the tangent. So, for products, what would happen? For products, exactly the same thing, only that the products appear as a function of time. So, R instantaneous, which is this, would be equal to dP over d of T, P being the product, preceded by a positive sign because the product is appearing as a function of time. Okay. Then we moved on to the initial rate of the reaction. So, initial rate, again as the name suggests, is at the very beginning of this reaction, at the very start of the reaction, okay, which is very close to time 0. Time 0 is very much at the initial point of the reaction. Okay. So, you can see from here the initial rate can be obtained from the slope of the tangent at that point. Similarly, we can do the same thing for product, again at time 0, you see the product is gaining as a function of time, that means it is coming into being, into existence as a function of time, and what we are doing is we are getting the initial rate by drawing a tangent at the very early time point for the product. A couple of other points we also mentioned about this initial rate. It is preferable to do the initial rate calculation based on product appearance, as it is mentioned out here, and this is because remember, when you have no product to start with and you have reactants to start with, and suppose your reactants are colored, your products are also colored, having a different color. Okay. Now, if you are trying to get this initial rate by looking at the change in concentration of the reactant, then what would happen is, because it is the initial rate, the change would be so small that you might not detect much. But however, think about the product, if there was no product to start with, right, but the moment some product appears, you see a visible change out there because there was no product as such, and suddenly some product came into existence, and hence looking at the product is always a better option if you are going to calculate the initial rate. I hope I have made myself clear with regards to that. Then the initial rate calculation, as the second point says, has to be done very close to the starting point, that is often within 5% of the start of the reaction. Okay. So, except chain reactions, chain reactions are quite complicated, the initial rate line or the tangent will always be the steepest one, that means the one having the maximum slope, and it makes sense because at the initial point your rate of reaction is also the maximum, and hence the slope or of the line is the steepest. Okay. So, the last thing we were discussing that day was this dependence of reaction rate on concentration from here what we plan to do, as you would see, is go on to rate expressions. So, let us focus on this again for some time. So, what we said was that this is a typical reaction profile where we see the concentration of reactant R being given on the y axis and the time being given on the x axis, and obviously the R being the reactant, its concentration is decreasing as a function of time if you follow the blue line. Now, what happens is, if you take definite time points like say this T1, T2, T3 and T4 and try to calculate the instantaneous rates at all these essentially the slopes, what you will see is that the slope of this tangent AB is greater than the slope of this tangent CD, is greater than the slope of this tangent EF, is greater than the slope of this tangent GH. So, as it says, if the instantaneous rate is equal to the slope of the tangent and with a negative sign, negative referring to the loss of reactant, then what we see is that AB is having the maximum slope, followed by CD, followed by EF, followed by GH, which is having the minimum slope. Again GH being this, AB being this, AB is having the maximum slope, GH is having the minimum slope, and then in between we have CD and EF. Again, just to remind you of our previous discussions on slopes, that when I am referring to the maximum and minimum slopes, what I actually mean is the respective magnitude of those slopes. Okay? So, please always keep that in mind. So, then what does this tell you? It tells you something. What it tells you is that maybe the reaction, not maybe, the rate of the reaction is proportional to the reactant. So, let us try to put that in words. So, let us talk about this. So, from this from this graph, what we can conclude is the following, that the rate of, so I will just change the pen, reaction, the rate of reaction is in some way dependent on the concentration of the reactant. Again, the rate of reaction in some way is dependent upon the concentration of the reactant. Why do we say that? Again, let us go back to this figure. See, at time t1 I have a certain concentration of the reactant R, at time t2 I have a certain concentration of the reactant R, at time t3 I have a certain concentration of the reactant R, and so on. And as I increase my time, what is happening is that the concentration of the reactant is decreasing. Now, not only that, based on the slopes that have the tangents that we have drawn out here, you can see that along with the decrease of the reactant, along with the decrease of the reactant concentration, the slope is also decreasing, right. The slope of the tangent is also decreasing. So, for example, at time t1 where the amongst all these time points t1 to t4, at time t1 where the concentration of the reactant is the highest, the slope is also the highest. Then I go to the next one where the concentration has decreased a bit at time t2, then the slope has also decreased. I go to the last point t4 where the concentration of reactant is the lowest, then the slope is accordingly also the lowest. Hence, what we can write is, so the rate of reaction is in some way dependent upon the concentration of the reactant, then I add this word remaining. Remaining means whatever reactant is remaining after some of the reactant has gotten converted into product. So, I can write that the rate is equal to, or say let me write this not equal to, let me write this as a proportional sign, proportional to the concentration of reactant to the power n, right. So, let this be equation 1. Now, this is significant. What you are saying is, based on the graph or the plot you just saw, the kinetic profile you just saw, based on this what we are concluding is that the rate of the reaction is dependent upon the concentration of the reactant that is remaining, and based on that what we are saying is then that the rate of reaction is proportional to the reactant raised to some power, which in this case is n. So, what is n? So, what is n? So, n is a number which states exactly how the rate depends on the reactant concentration, right. So, this is important, it states exactly. So, this n states exactly the nature of dependence of the reaction rate on the concentration of the reactant. N therefore, is the order of the reaction, right. N is the order of the reaction, and we can go ahead and write, we can remove the proportionality and write that rate is equal to K times the concentration of reactant raised to the power n. Let this be equation 2. Okay. So, obviously, now you realize that this K is my constant of proportionality, and hence this one is called the rate constant. Okay. Again, this is a very important term. In chemical kinetics, which is the rate constant. So, what is then rate equal to? Rate is equal to the rate constant K times the concentration of the reactant raised to the power n, which is the order which tells us exact nature of the variation of the reaction rate as a function of the concentration of the reactant. Okay. So, what does this equation 2 tell us? What it tells us is this, that if n is equal to 1, then it is a first order reaction. Okay. If n is equal to 2, right, then we call it is a second order reaction. If n is equal to 3, likewise it is a third order reaction. If n is equal to 0, referred to as a 0 order reaction. If n is 3 by 2 or 3 halves, then you see it is a order which is fractional, that means fractional order of 3 halves. So, which means that if n is equal to 1, it tells that the rate is equal to k times reactant raised to the power 1. Then if n is equal to 2, it tells us that rate is equal to k times reactant raised to the power 2. Okay. If n is equal to 3, it is a third order reaction, k times reactant raised to the power 3. If n is equal to 0, then this value of n is 0. So, which is called a 0 order reaction. Order values, that means n values can be fractional, and this is what you see is n equal to 3 by 2, then I put 3 by 2 out here. But in a nutshell, what this is telling me is how the rate is varying, or how the rate depends upon the reactant concentration. Now, that is the most important part. Now, suppose I have a reaction including 2 reactants that are A and B. Okay. And what I found out was, by doing an experiment, this the ways we try to find out the orders, we will discuss those a little bit later after going to the integrated rate laws and all. But suppose we do an experiment or sets of experiments to find out the rate or order of this, and we say that the rate is equal to K into concentration of A into concentration of B. Okay. And I would say that this would be, let us see reaction, equation number 3. If I put in, now the way I read this rate equation is, I say that this reaction is first order with respect to A, or also I mean first order with respect to A, also it is first order with respect to B, because you see rate is equal to K, the rate constant, times A raised to the power 1, B raised to the power 1, is not it, right. Hence, I say that it is first order with respect to A and the rate is first order with respect to B. So, if you take A, then how the rate will vary? It will vary as being first order with respect to A. If you take B, then how will the rate vary? The rate will vary as first order with respect to the concentration of B. Then what we can say is that the total order of the reaction is 1 plus 1 equal to 2. So, what does it mean? That the total order of the reaction is the sum of the exponents, where the exponent for A is 1 because first order with respect to A, exponent of B is 1 first order with respect to B, but the total order, so as I say the total order here of the reaction then is 1 plus 1, which is equal to 2. Again, please remember this is also very important. It is being a second order reaction, the order, the way this equation has been written, the order is equal, this expression has been written, the order is equal to the sum of the exponents of the orders of the 2 reactants, that is 1 for A and the exponent for B being 1. So, 1 plus 1 is equal to 2. If you take another example, say where rate is equal to K A B, this before. So, what are you saying here? So, here experiments, or by doing experiments we have found out that the rate for a certain reaction is equal to K times the concentration of A raised to the power 2 and concentration of B raised to the power 1. So, we again say that it is second order, right, with respect to A, first order with respect to B, right, and as before the total order is equal to 2 plus 1 is equal to 3, right, like before. So, the total order of the reaction is what? The sum of the orders of the individual reactants. That is exactly what you see out here. That was what happened in the example before, where it was rate is equal to K times concentration of A times concentration of B, and what is happening out here is, it is here the rate is equal to K times concentration of A to the raised to the power 2 times the concentration of B, hence the total order is 2 plus 1 equal to 3. Okay. So, then these equations the equations we have written out here. So, for example, the equation you saw out here and the equation we wrote out here. So, if you can write the equations in a very general way, say rate is equal to K, right, times reactant raised to the power say n, or we can write rate is equal to K times reactant 1 raised to the power say alpha, then reactant 2 raised to the power beta. Okay. So, it is going out of the margin. So, in this case we see the rate is equal to K times reactant raised to the power n, one single reactant raised to the power n, the order. In the second case we see rate is equal to K times reactant 1 raised to the power alpha, reactant 2 raised to the power beta, that means there are 2 reactants. So, these sorts, I mean if I can say this is this is equation 5, you can say that this is equation 5 and this is equation 6, then we can say that these are referred to as rate expressions. Okay. These are referred to as rate expressions or rate equations. Okay. Either rate expressions or rate equations, right. And what are they telling you? What are they telling you is how the individual reaction is depending upon the component species. If it is one species raised to the power n, if there are 2 species say, then one of the species raised to the power alpha, one of the second species raised to the power beta, these being the individual orders of the specific reactants. What we can now generalize, saying that if I have a very general equation of the type A plus B plus C going to P plus Q plus and on, if I have equations like this, then what I can do is I can say that the rate expression or rate equation is equal to K, the rate constant, times concentration of A raised to the power alpha, concentration of B raised to the power beta, concentration of C raised to the power gamma, and so on and so on. So, if this is my rate expression, right. So, if this is my rate expression, say let this be equation 7, if this is my rate expression equation 7, then the total order of this equation is equal to alpha plus beta plus gamma plus the rest of the exponents. Okay, that is your total order, and K is referred to as the experimental rate constant. So, order is an experimental quantity, so is the rate constant here, and having a very general, having written a very general equation like this, where A, B, the small letters being the coefficients, so the big letters signifying the reactants and the products. If the rate expression is given like this, right, where the exponents show the nature of dependencies of the individual reactants for the rate, then the total order is given as a sum of the exponents, which is alpha plus beta plus gamma, and k being the experimental rate constant. So, again before I move forward, this is a very general form of this rate expression, and being general form, it typically holds throughout. Now, there are some key points you have to remember. The key points are like this. What are some of the key points of the rate expression you just saw? So, there is one concentration term for each reactant, one concentration term for each reactant. See, for example, where we had the reactants A, B, C, right, there was one concentration term for A being a reactant, there was one concentration term for B, there was one concentration term for C, and so on. Then each concentration term is raised to a particular power, right, as we saw alpha, beta, gamma, and so on. So, as again each concentration term, say A was raised to the power alpha, B was raised to the power beta, C was raised to the power gamma. If I do a kinetic analysis, what would I aim to do here? Again, I am doing a kinetic analysis. What do I mean by that? If I am doing this analysis, what I am trying to get is, I am trying to find the value of alpha, beta, gamma, and so on, right, because I am doing an analysis. By doing this analysis, I am trying to find out what these respective exponents are, alpha, beta, gamma, and also by doing this analysis I am finding the value of k, which is the rate constant, the k which is the rate constant at a certain temperature, at a certain temperature. So, when you are doing a kinetic analysis, what we mean by that is, of any reaction, what I mean is that I need to figure out the respective orders for each and every individual reactant involved, and once I have done that, I also need to figure out the rate constant k at a particular temperature, because remember, rate constant is a constant, but it does depend upon temperature, right, and hence whenever we are trying to do this analysis, we have to make sure that we do it at a certain constant temperature, because the rate constant is defined only for that temperature. The moment the temperature changes, the rate constant value will change, because it has a temperature dependence, a feature, a very important feature of chemical kinetics, which we will discuss later. Okay. So, this was whatever we have done up till now, starting from the average rates, instantaneous rates, and so on. So, from there you see we have slowly moved on. We looked at this we looked at this initial rate. After that, we looked at how the slopes would differ at each and every time point, and from there we got an idea that the rate might be depending upon the concentration of the reactant remaining. Okay. After having done that, we started working on the rate expressions, how the rate expressions should be written, what should be included in the rate expressions. So, now the rate expression we know it has the rate constant, it has the individual concentrations if there is only one reactant species, then there is only one concentration. If there are many reactant species, then there will be many concentrations like A, B, C, but each of these would have to be raised to a certain power, or they should be having certain exponents. These exponents are referred to as the orders of the reaction with respect to each and every individual reactant. If there is only one reactant, so that is rate is equal to K times A to the power n, that n is the order of the reaction. If there are more than one reactants, there is multiple reactants, where we just saw rate is equal to K times A to the power alpha, B to the power beta, C to the power gamma, and so on. Then the total order of the reaction is alpha plus beta plus gamma, and like that. Okay. So, these are some basic fundamentals which have to be absolutely clear before you go ahead and start working with the concepts of chemical kinetics. Right, having done all these, I will shortly look at the units of rate. We know that what is rate? Rate is essentially the change of concentration with time. So, I can see the unit would be concentration over time. So, if that is what it is, the units are. So, if your concentration is expressed in moles per liter, it is a molar concentration. So, time can be anything, time can be second, time can be minutes, and so on. See, for example, if concentration is in molar units or moles per liter, then what would the unit be? The unit of rate is over time, or m time inverse, or we can write moles over time, or mole liter inverse time inverse. Remember, time can be anything, time can be seconds, time can be minutes, time can be hours, depending upon the type of reaction you are studying or looking at. So, this is how the units would be written if the concentration would be expressed in molar units. However, for gaseous reactions, one of the common ways of expressing this is in atmospheres over time, or I can write atmosphere time inverse. Okay. So, now if I say that if time is in seconds, so if time is being expressed in seconds, say, then what I can write is for the molar unit, for the molar unit where the concentration is expressed in moles, I can write mole second inverse or mole liter inverse second inverse, and for gaseous I can write atmosphere second inverse, right. So, that is why this is very straightforward. Why? Because you know that the rate is how the concentration is changing over time. So, that is what you have just done. If your concentration is in molar units, you put in molar units, moles per liter. If your concentration is in atmospheres, for gaseous reactions you put in atmospheres, and so on. Now, let us look at the meaning of rate expression. So, meaning of rate expression. Now, this is again very straightforward. It is the extension of the discussion we just had. So, see, for example, the first one, if rate is equal to K times say the reactant A, K is equal to A K times reactant A. So, we obviously know then that this is a first order reaction. Okay. There is a first order reaction, which means that if concentration of A is increased, if concentration of A is increased by a factor of 2, say if the concentration of A is increased by a factor of 2, then the rate also increases by a factor of 2. Straightforward, right? Rate is equal to K times A. So, increase concentration A 2 times, the rate also increases 2 times. Similarly, if concentration of A is increased by so this by a factor of 6, say, that means the concentration of A has been increased 6 times, then rate is also increased by the factor of 6. Okay. So, when concentration of A was increased 2 times, rate was increased 2 times. When the concentration of A was increased 6 times, rate was increased 6 times. This is the concept behind a first order reaction. However, if we take this case where the rate is equal to K times the reactant A raised to the power 2. So, obviously, we say that it is a second order reaction. When we say it is a second order, what do we mean? We mean if concentration of A is increased by a factor of 2, then rate is increased by a factor of 2 raised to the power 2, which is 4 difference. You see, first order it would be 2 if it is 2 raised to the power 1, second order it is 2 raised to the power 2. Similarly, if concentration of A is increased by a factor of 6, then rate is increased by a factor of, remember it is increased by a factor of 6, right. So, now it is 6, you have raised it, but then to the power 2, which is 36. Again you see the difference. If this was a first order reaction, the rate would be increased by a factor of 6 to the power 1, which is 6. This being a second order reaction, the rate is now increased by 6 to the power order, which is 2, that is 36. Okay. So, these are some things we should be able to tell right away when you look at the rate expression. Then if we have rate is equal to K times concentration of A to the power 0, remember now n is equal to 0, which means it is called a 0 order reaction. that means the rate is 0 order with respect to the concentration of the reactant, which is A. So, which means no matter what the concentration is, no matter what the concentration is of A, the rate will remain constant, right. So, this being a 0 order reaction, k raised to the power 0, it means that the rate has no dependence whatsoever on the concentration of the reactant you have taken. So, you can vary the concentration of the reactant many fold, many times, but the rate is absolutely not dependent on the concentration of A. So, like we did worked out the units of the rate, we can also work out the units of rate constant. Again, this is very simple, right. This is very simple. We need to know the rate expression. Say for example, I do a first order reaction, okay. I do a first order reaction, okay. And in this first order reaction, we know that the rate is equal to k times concentration of A, right, very simple. So, because it is a unit of rate constant I am looking at, right, remember it is a unit of rate constant I am looking at right now, not the rate, but the rate constant. So, what is k? Then k is equal to the units, the concentration of A over the unit of rate, right. Now, the concentration of A is say expressed in molar concentrations or moles per liter, moles per liter, that is the concentration of A. We know that the concentration of the unit of rate we just derived before, it is what, sorry I extremely sorry, I just had it reversed. So, just hold on. So, let me take let me actually cut this, hold on. So, this remains the same, I wrote this one wrongly. So, what I should write is extremely sorry. So, k is equal to rate over A, okay, extremely sorry for that. So, rate is equal to k is equal to rate over concentration of A, and the concentration we knew say is mole liter inverse, and then what we are doing is we are putting the unit of rate out here. So, we go to the next page, we write it a little in a better way because I have done some cancellation. So, k is rate over concentration of A, the concentration of A is mole over liter. So, moles per liter or molar concentration. Now, remember rate was concentration over time. So, I will be writing moles liter, then time inverse, okay, and hence the unit of k will be that of time inverse, right, because these moles per liter cancels from the numerator and the denominator. So, the unit of k is time inverse. So, if it is second, so it can be second inverse, it can be minute inverse, it can be hour inverse, H standing for hour, hour inverse, and so on, right. So, hence for a first order reaction of the type rate is equal to k times A, for a first order reaction rate is equal to k times A, the unit is the inverse of time, okay. So, likewise we go to second order reaction. So, here let us take this example where rate is equal to K times concentration of A raised to the power 2, 2 being the order, in this case 2, hence second order. So, therefore, K is equal to rate over A squared, okay, rate over concentration of A squared. Okay. So, again what was rate? Moles liter inverse, concentration being expressed in molar units or moles per liter, then time inverse over what do we have? We have the concentration of A raised to the power 2, hence we would be having moles liter inverse raised to the power 2, okay, and thus we will be having as, so one of these would cancel out, right. So, this will go on top. So, I will be having mole inverse liter time inverse, and the better way of writing this, a better way of writing this is, so you understand, right, this is moles per liter, one of the moles per liter is cancelled out, you are left with one more moles per liter that goes on top. So, it becomes moles mole inverse liter time inverse. Now, the general way of writing this is that, see, this liter is having the positive exponent. So, you always bring the positive exponent first. So, you write liter mole inverse time inverse. Okay. So, this then is the unit of the rate constant for a second order reaction. Again, the time can be anything, you can replace it by second, you can replace it by hour, you can replace it by minutes, depending again upon the reaction you have in hands. And as I told you again, this, the way it is written is this, you just make sure this is not wrong, but what you just make sure is that a better way of expressing this is that the one which is having the positive exponent is written first. So, I have taken later first, it is raised to the power plus 1, and negative exponents are written later. Okay. So, carrying on with the same concept, if I go for say a 0 order reaction, say, now if I go for a 0 order reaction, as we have seen before, rate is equal to K A raised to the power 0, right. Now, because it is raised to the power 0, anything raised to the power 0 is equal to 1, hence I can write rate is equal to K. So, what does it mean? That means the unit of rate constant is equal or is that of the unit of rate, because the rate is equal to K. So, then the unit of K is equal to moles liter inverse time inverse. Okay. Again, please take care of one thing, here you see the mole is having the positive exponent. So, I have written this in first, and then the liter inverse and the time inverse they come in later. Okay. So, with respect to the units of the rate constant, so this is how you always figure out. See, there is not this this is not something that you have to memorize. Once you have the rate expression in front of you, you know what the unit of rate is, always concentration over time. You know the the units of your concentration for the reactants, and given the rate expression you can always do this and find out the corresponding unit for the rate constant. So, there is minimum memorization, maximum concept or understanding. So, let us do a quick example. Okay, what does this example say? So, the example says that there is a reaction where, so I have a reaction say, well, let this be A. So, I have a reaction which is first order with respect to A and first order with respect to B, and the reaction is happening between A and B. Okay. So, now what you are being asked is, give the rate expression for this, and you can assume time to be expressed in minutes. Okay. So, you have said that there is a reaction between A and B, the reaction is first order with respect to A, first order with respect to B, and the time which you should take, the unit of time is minutes. Okay. So, this will be the last thing I am going to discuss in this class today. So, then based on our previous discussions, I can write the rate of the reaction is equal to K times concentration of A raised to the power 1 times concentration of B raised to the power 1, both being first order. So, you can write A B, this is the rate. Okay. So, the moment I have written this, I can, though it was not asked, then the overall order or the total order is 1 plus 1 equal to 2, right. And then because this is what, second order reaction, then what can I write? I can write is that the unit of K is equal to rate over concentration of A, concentration of B. I know that the rate is moles liter inverse, and because the time was minutes, minute inverse, and then I have the concentration of A expressed in moles or molar concentration, and this one also in molar concentration, is moles per liter. So, the moment I do this, I can see I get this is equal to liter mole inverse minute inverse. This was an example where you have been told that the reaction is first order with respect to A, first order with respect to B. Write the expression, the total order is 1 plus 1 equal to 2. Once you have written the total order, now this was simple because you had done this before. We had done this before in the sense that we had taken rate is equal to K times A raised to the power 2, but here we have taken two different reactions, each raised to the power 1, but total order is 2, and hence you get again the same value of the unit for the rate constant. Okay. We will stop here and we will carry on from this place in the next class.